So, tonight I'm going to tell you a little bit about Kubernetes, which is an evolution of what we do with cluster computing at Google. So for the past 15 years, we've been building what effectively is the largest cloud on the planet and only been using it internally. So we use this to power search, YouTube, all of the Google services. We've got a number of data centers worldwide you can see on our website. We've got a lot that you can't see, obviously. But we've really sort of advanced the state of the art in terms of cluster computing, published a lot of academic papers, and a lot of the research that we've done has led to some of the products that you see today, both from myself and from others. So, containers, we want to be able to run a lightweight Linux environment. I'm going to assume that most of you have sort of familiar with Docker in some way, or else some of these talks coming up will need a little bit of background. But to us, containers raise an abstraction level. So they let you separate your application from the place where it runs. And if you use VMs, you sort of interact with idealized hardware. So you say, this is what we think a computer should be. But your application, the server stack that it runs on, it's all kind of mixed together. And you have to deploy these things in a very sort of commingled way. So with containers, you can create an idealized static Linux environment and sort of lift you up the level of abstraction where you, as a developer, are just dealing with your application. And you're dealing with it in a fashion where you can repeatedly deploy an application onto your laptop, onto a test cluster, into production, running the same environment all the way through. So that's the basis of Docker's obviously gone 1.0 recently, so there's a lot of interest in this. Containers are introspectable, so you can run a container on a machine, and you can actually have the host outside of that look in and look for things like performance characteristics, CPU usage, memory usage. And then you can also restrict what the container is able to use with some of the kernel facilities such as C groups. So we've been using containers at Google for around about 10 years. We wrote the C groups patch and released that in 2004. So our cluster computing system at Google runs a very sort of portable environment, very common threads through things. Resource isolation lets us identify workloads which we want to run high priority, run real time, and then also identify workloads that we want to run in batch. And we don't care where they run, and we can move them around as we need to prioritize high priority jobs. It means we can run things very predictably. We can efficiently overcommit, so we can have an environment where we know it will scale up for the tasks that it needs to run for real-time jobs, and then back things out if we need to for batch. So overnight, we can take these environments, we can run MapReducers on them in their spare capacity, and it's very easy because these effectively run as processes to be able to terminate them very quickly when you need the performance in your other environment. We also get to do great resource accounting, so we can very easily look at the usage across the entire fleet of any particular application. And very important thing to note, everything run in production at Google runs inside a container. And we start over 2 billion containers every week at Google. Even our GCE instances that you can rent from us run inside a container. And that's an example of an area where we can say we don't overcommit these containers. We have resource limits which allow you the full access to them. So our managed container stack looks a little bit like this. We have a base operating system which runs a container manager layer on top of it. We have the system container, which is statically defined, and then we also have a number of dynamically defined containers that run on a particular node, with an external scheduler that will look for work requests and run tasks on the cluster. The scheduler refers back to the system container to ask things like, how's the machine doing, what tasks are running? And we want to be able to run that in a very declarative way. So we want to be able to, instead of saying, here's something, please put that on that server over there, when you start running at the scale that we need to run, you want to be able to say, I want to have 100 of these running somewhere within this cluster. And you might say, well, I want to have no more than 2 of them failed at any time. So if one of them fails, have it restart something somewhere else. So for anyone who's sort of familiar with modern configuration management, it's a very similar ideal. It's very repeatable. You just say, this is what I want, you set it and you forget it. It's easy to update containers, which we'll show you in a little demo later on. But it's a little bit hard if there was a downside to it, then you'd say, well, seeing as you are not making these changes yourself, you're asking the machine to reconcile the state for you, you need to go back and look at the introspection layers to tell whether or not something's actually been done. So as I say, it's been over 10 years we've been using containers in our clusters internally. We started using limited isolation about 10 years ago. Sorry, it was 2006 that C groups were released. We released a cluster driver called LMCTFY, or LMcTuffy, in 2013. So it's conceptually similar to LXC. It's another variant on the same ideas. And what we're doing is we're taking a lot of the ideas from that and trying to merge them upstream into Docker's libcontainer. There are a few things, if anyone's interested in the lower level details of how the resource management works, there's open source, it's available online. And then this year we've released a couple of important things. So C-Advisor lets you look inside, does the introspection for you on top of Docker containers, and Kubernetes is the system I'll tell you about in a moment. The containers we use at Google, we've been running for a lot longer than Docker's been around, so we do things subtly differently in some cases. So when developers push code to our clusters, they bind mount to the host operating system. They build a binary, static binary, they sign it, and then it gets pushed out to the cluster. And they have standard locations for its interface to your cluster manager. Your clusters will have a standard logging and monitoring API, and your application just calls into that, so you don't need to worry about, effectively, these things can be considered stateless for workers, and as much as possible, all the information is kept outside of the cluster, inside of the containers. So Docker is a lot more hermetic. You get the entire CH root. You get everything you need to run this, which means you can run it locally. It's fantastic. It's what we would have done if we had the facility at the time, and it's an influence, obviously, as to how we'll do things going forward. And it lets you use the standard operating system tools that you're familiar with and your package managers. Why you should care? Well, there's sort of three things that we find that people get aha moments when they start dealing with containers. First one is that it's the same wherever you want to run it. So it's reliable, you copy it from place A to place B, and assuming that it copied correctly, it runs. All it needs is the interface of a kernel. Any modern kernel will do. You don't need to worry about, I'm running on the same operating system underneath. We really want to abstract that away. Second thing, obviously, is that makes it portable. You develop here, you can run on Google Compute Engine, you can run on Amazon, you can run on Rackspace. You've all got $500 of SoftLayer credit, which I'd encourage you to download Kubernetes and run it there. And this lets you start looking at how you might architect an application if you didn't have to worry about some of the previous constraints to say, well, we want to mix in services, and it really helps you if you want to move to microservices and more some microservice-oriented architecture. Because it's highly automatable, you get to start managing actively. So we talked about declarative management before. You can efficiently pack where you want your tasks to run. You can look at what the usage is on any of your machines at any given time, and you can pack things in a lot better fashion. You can actively tune your environment based on the things that are running and the performance characteristics that you want to offer. It's much easier to do continuous integration. And you can have a cluster that's sort of actively monitoring and self-healing and watching itself for errors. It knows what you've asked it to be, and it will keep running in that way. So our node container manager, the two base layers of this, so we have an operating system and the container manager. Inside GCE, Google Compute Engine, we provide this as a container-optimized VM image. We have a standard manifest file format where we say this is how you want to run a container. And we provide monitoring and restart. So you just deploy containers on top of this, register them with the system using the manifest, and it will make sure that they keep running. That is, of course, what the scheduler will do. Inside the VM, it looks a little bit like this. So we have Google provide the operating system and the monitoring and the logging agent. On top of that, we have an init system which runs standard SSH and Docker so that you can access the VM. And then the only thing you need to worry about is the bit here in blue, is the container environment and your own application. We get the bit on top. We want to be able to take these containers, which are things that exist only in one place, and we want to say, well, we want to have 100 of them. We can't all put them on the same machine. We want to have a network of machines. So the scheduler exists outside of each individual node, and it takes containers and puts them on the machines based on whatever the characteristics are of the scheduler, be it just a round robin, a very simple approach, or be it looking into each machine saying, I want to make sure that no more than 3 of this particular task are running on this particular machine, anything along those lines. So that brings us to Kubernetes, which we released earlier this year. Kubernetes is an open source application. It's Apache licensed. It's written in Go. It's static like Docker. It runs anywhere. And it lets you manage your container fleets as applications, not machines. So some of you may be familiar with a paper called Google's Omega paper talking about cluster management. This is the engineering teams who built this. A lot of the guys on that had taken these approaches to say, if we were to build this to take container abstractions, to take Docker and run on modern cloud operating systems, what would we want this to look like? And they're the guys who've come up with Kubernetes. So you'll have a network of machines. You'll have a cluster. In this case, we've got 7 machines, and they're all running GCE virtual machines with the container agent on top. And then we have a master machine that runs on top of it. So it's much easier because you're now no longer maintaining the operating system. All you do is you interact with the big red box up the top. In general, we don't find that people want to deploy just individual containers. We want to deploy a concept of a few different things that relate together. So we call that a pod. You might have a web server application and the data files that relate to it. You want to have them in 2 different containers, but they're linked together so that you don't need to worry about redeploying the application server if you change the files. An example we use a lot is a web server will write out log files, and it will need to have a log roller that will be looking at them and uploading them to a monitoring service like BigQuery, or simply rotating them. So we're going to represent that as a front-end pod in this. So we have a pod made up of a number of different containers that you specify in a manifest. So you might say, all right, well, I want to run a front-end pod on Kubernetes, and that's fantastic. But very soon you'll find, say, we want to run several dozens of things. You'll end up with pod overflow, where you have a number of different services that you run on top of your cluster. And what you want to do is you want to be able to organize these. You want to be able to turn them into services, and you want to be able to control replication of them. So we use the concept of labels. You may have the green highlighted ones here are the front-end services. So these are anything that's running what we've defined as being front-end code. But we may also want to say that some of them are production containers, some of them are canary containers. We may want to have a different load balancer that says 10% of our traffic goes to the canary instances. If that code is good, we'll move it on to others. So each pod gets labels, which you can select on, and then use some of the higher level Kubernetes services. One service we have is a Replica Controller. The Replica Controller lets you define a template and say, I want to have these pods with these labels, and I want to make sure that there are a certain number of them. So you might say, well, I want there to be 4, and the scheduler will turn on 4 for you. If later on your workload decreases, you want to say 1, you change your file and you push it to the master and say I only want 1 replica. And then it will go through, it has a consistent, use etcd for a lock service, so you can go through and say, I'm going to terminate, the service will go through and say to you, I'm going to terminate 3 of these. Or we need to scale back up again, we go and say we want another 2. On top of that, we can run services. So a concept we have in Kubernetes is each pod has its own IP address. So there's a single IP address per pod, and the containers that you run in that pod, you have different ports. So you can use that as a way of guaranteeing that you don't need to do service discovery between these things. You just talk to localhost from your container on the port that you know that is in that pod. Outside of this, we use a load balancer. It's currently implemented in software, but you could see that it also connect this to a GCE load balancer, and you could also fork the code and put in any logic that you like, where each machine that's running, whether or not it's hosting that pod, it's hosting the service. So all you need to do is refer to the service by its port number, and then it will find an instance that's running of that particular pod and route you to it. I have a little demo, which would be a lot easier if I had a computer to drive, but we're going to show you the screencast version and see how we go. So David's just going to switch over to that now. I'm going to pretend I'm typing as we go through with this. Okay, so in this example, we have a Kubernetes cluster that's running on GCE. So we'll see that we have one master machine and 5 minions which it can schedule work onto. We talked about the replication controller. So we'll start a replication controller running this here script. In the window that you'll see pop up there, we have a little interface which will show the running pods inside our cluster, and it will show you effectively the work that's running on them. So there's running a little web server, they're serving a unit of an image basically. So now the YAML that comes back from the server here, we show that we've said we want to have 2 replicas. We want to use the container, we want to name the container, give it the label of update demo, and use that Docker image, which I pushed to the Docker Hub previously. And so now we have 2 of them running. So 2 of the minions have had a container pod scheduled onto them. This pod is currently only running 1 container, runs Nginx, and it shows you the image. So let's say that we have a very popular service and we want to size that up, we want the scale now. So now we come back, our desired state is we want 4 replicas. So this is return from the service. And then if we switch back to that window, we now have 2 more containers have been scheduled and are running on 2 different machines. So these are 2 more pods running those containers. Because this is actively managed, if I were to go in and kill one of those pods, so pretend there was an error in it, or it was removed just using the REST API in this case, you'll see that that container has now terminated. And what will happen is the replication controller will say, I've only got 3 of these. I've been told I need to have 4. And it will start a new one. It will start the container, and it will start serving the correct image. This is an SSH session onto one of the minions. This is actually one of my containers that's running, the Nginx image that's running my little Nautilus shell demo. And if I kill that, again, and we go back to, you see now the container has been killed. And in the service window, you'll see that the image, it will spin up the new container. Let's say click back to the window in the background, check to see that the container has started on the machine, and there we are, it's recovered from that failure. One of the great things you can do when you use a cluster system like this is we say, I want to run an update across all of these nodes. So this particular thing is going to change the Docker image that I'm running. And I'm just for the purposes of showing you quickly, we've accelerated this to do a rolling update where it will kill one of the nodes every 10 seconds, and then the replication controller will automatically heal. In production, you might do this, say, once every 30 minutes, roll out various nodes and use a different load balancer to change between them. But just for this example, we can see that we've killed a node, and now we're serving the different container instead, which has different data in it. So this will go through every 10 seconds, killing one of those nodes until we have the container, the cluster in the state that we want it to be. Looks like we're almost consistent. Great. So now it's very easy. We just want to stop the service running, clean it up, and we just run the script which stops the replication controller, which will remove all of the pods that it's scheduled, stop the containers running, and return us to the empty state that we were at the beginning. So there we are. First of all, the containers are cut down, they stop serving, and then their pods are removed. Okay, that's the demo. If you don't mind changing back to the slides, please. There's a little diagram here which you can see on the Kubernetes website. It's probably not visible enough to go through it now, but it just shows the architecture of how everything works with these minions here on the right that are running the node manager, service proxy, and then the various pods that have the containers, and with the service on the left there. So Kubernetes has had a fantastic uptake with the community. So we're delighted to say that Red Hat are launching the OpenShift version 3, their platform as a service, is going to be based on Kubernetes. We've had great uptake with CoreOS. We're getting lots of contribution. We're using their etcd, and they're starting to look at ways to contribute some of their networking framework to us. There's been a recent partnership with Mesosphere where we're able to deploy Kubernetes on top of a Mesos cluster. We've had partnerships with some non-traditional people as well. So the first Azure hackathon was getting Kubernetes running as a way of scheduling Linux workloads on top of Azure. We've worked with VMware to make sure that it's possible to run this very well on your own local hardware. And obviously under the covers we use and we work with Docker and with SaltStack to do the deployments. So we've had a fantastic uptake. We've had over 3,600 people have started the repository, so it's now the biggest configuration management, most popular configuration management related thing on GitHub. We've got a number of authors within Google, but we're getting lots of contribution from outside. We'd love to get people to get involved. It literally takes 2 minutes to download this code, push it up, and get a 5-node cluster. There's one script you need to run. The code to run that demo is online as well. We've got a new website just launched. I had this t-shirt shipped over from Mountain View this morning, but kubernetes.io. You can go there. It's a link to a GitHub repository and also some documentation. So I'm going to leave you with here an offer with $500 credit to get started on Google Cloud Platform. You can use that to spin up a Kubernetes cluster. You can use that to do big data analysis with BigQuery, anything that you like. You need to go cloud.google.com/starterpack, and you click apply now, and the code that you need is DevOps-con. So I'll just give you 2 seconds to take a photo of that. And as I say, we'll email it out. I know that it won't be the first $500 credit you've been emailed, but we'll make sure that we get you guys all started. So thank you very much. That's the end of my talk. It's been a pleasure. Please come and have a chat with me afterwards. We'll get you started. Thanks.